The dark matter problem reflects a fundamental system error in our geometric map of the universe. Current equations only balance if we invent a massive amount of invisible mass to act as a placeholder. In this model, matter acts like a record needle. While standard cosmology treats space-time as a passive surface, the missing mass problem disappears if that surface operates with the vortical tension of a tightening Fibonacci screw. The standard lambda CDM model forces a torsion-free assumption onto the universe. It treats the geometric grid as a static, non-twisting medium. Solving the mystery of underlying geometry requires migrating cosmology from a torsion-free space to a Riemann-Cartan manifold. Anderson Spiral Torsion Theory, or ASST, provides the framework for this geometric update. At its core, ASST introduces a dynamical vector field called the spiral director, or K-mu. Fixing the geometric kernel with this torsion leb balances the gravitational equations without the need for invisible particles. We can derive the ASTT framework from first principles by defining its core mathematical structure. The theory begins with the formal ASTT action equation, where the torsion tensor is embedded directly into the Riemann-Cartan manifold. The golden vacuum constraint, located at the base of the functional, sets a strict boundary condition for the field. This constraint forces settling into a state of permanent tension, proportional to the inverse of the golden ratio, phi. This constrained vector field natively generates a global torsion web that acts as the baseline geometric tension of the universe. Establishing this geometric limit at the vacuum level provides the mathematical scaffold required for large-scale cosmic structure formation. The effects of this constrained torsion field are most visible at the absolute quantum limit. At this scale, gravity operates as a chaotic, tightening, three-dimensional Fibonacci spiral, strictly bounded by the optimal packing density of phi. We define the bridge between this quantum behavior and the macro world as spherical Phyllotaxis. On a foundational level, trillions of these microscopic quantum spirals overlap and interact within the packing lattice. This massive overlap eventually reaches a point of statistical averaging, resulting in the macroscopic appearance of a smooth, symmetrical gravitational field. General relativity's smooth spherical geodesics work locally because they describe this statistical average, even if the underlying quantum mechanics are chaotic and spiraled. Macroscopic gravity emerges as a statistical result of overlapping quantum Fibonacci spirals, rather than a fundamental spherical force. Scaling up to the size of a galaxy, we must account for the interaction of these massive spherical wave ripples. Interacting wave functions create residual geometric seams, forming the macroscopic torsion web. These structures follow the Sturm-Liouville eigenvalue problem derived from the K-field wave equations. Galactic spiral arms emerge as strictly quantized interference modes of the background torsion field. The lowest energy state for these interference patterns is the m = 2 mode, which dictates the prevalence of two-armed spiral galaxies. This geometric structure resolves the primary contradiction in the standard model, the anomaly of flat galactic rotation curves. The macroscopic torsion web produces a localized logarithmic tension at the edge of the galaxy, labeled here as lambda phi. This tension term integrates directly into the updated velocity equation, altering orbital mechanics at extreme distances. Geometric tension natively holds outer stars in place, removing the mathematical requirement for dark matter halos. We can scale the model down to the planetary level to address a localized thermodynamic anomaly ignored by standard astrophysics. Earth's heat budget presents a long-standing contradiction. Its core remains molten over billions of years, despite lacking sufficient radiogenic heating to stay that way. Within this framework, massive planetary bodies sit inside local torsion hotspots of the global Fibonacci spiral. Every planet has a specific misalignment between its rotation vector and the localized background torsion vector. This angular misalignment generates continuous axial friction. As the planet spins within the torsion field, it produces physical shear that converts into internal heat. This continuous geometric shear provides the 47 terawatts of power required to maintain a molten core. ASTT unifies galactic kinematics and planetary geology under a single geometric mechanism, demonstrating cross-scale predictive power. Pushing the model back to the cosmological origin reveals a state existing before matter and metric states. Primordial geometry acted as a tension reservoir, collapsing inward toward perfect self-similarity. This collapse continued until it collided with the absolute mathematical limit of the system, the Phi-Limit. At this limit, the stored torsion energy reversed polarity and unwound explosively in a topological phase transition called the snap. This unwinding occurred in sequential layers, where each step of the spiral's expansion created the directional order we experience as time. The torsion web itself physically constitutes the expansion of metric space, replacing the Big Bang singularity. To move from theory to observation, we can outline concrete paths to test and falsify the ASTT model. These implementation matrices are designed for integration into standard cosmology Boltzmann codes, like class and camp. These new constraints allow the perturbed modified Einstein equations to directly compute the matter-power spectrum. The primary diagnostic signature of the theory is the Fibonacci sound speed, denoted as c sub s squared. This geometric sound speed dictates the exact spacing of the acoustic peaks within the early universe's cosmic microwave background. We can now compare ASTT's predicted CMB peaks against established models to see which best matches observed data. This provides a mathematically explicit, testable backbone ready for large-scale n-body simulations. Embracing the golden constraint and torsion elevates cosmology from patching system errors to identifying fundamental resonance.